Greetings, wanderers. You've found yourself on the far shores of yet another BERD Core Special Topics talk. This is Statistical Rules to Tape to Your Forehead, talk number 6. I'm Dr. Mark Williamson of the Biostats Core for University of North Dakota. Okay, so the goal of this latest talk is to present a clear list of rules for statistical analysis that are 1, useful, so they'll help you out, and 2, memorable. They're sticky. They'll stick to your, not just your forehead, but to your mind in a more abstract way. So where these come from, these rules, how I develop them. For one, they're from my personal experience, so what I find is useful and helpful when I'm doing analysis, as well as what I was sort of taught and learned through my courses. And then also experience of others. There's some great resources I'll have for you that have similar or parallel types of rules or lessons. Now, some caveats for this. These rules are not exhaustive, inviolable, or strictly linear. That is, there might be more rules you need to do for specific analyses. Maybe some of these rules won't apply to your specific analyses. And, you might have to do these out of the order or switch them around, go back and forth, rather than sort of 1, 2, 3, 4, etc. in that order and not going back and forth. So these are kind of fungible. So rules, that sounds like a good name. This might be better to say, call them guidelines or something like that. They're not strictly followed all the time, but I like the term rules, kind of helps stick in your mind. So let's just use that term for now. And then, so we'll walk through all the rules here in the following slides, and then I'll follow up with an example using shark data to kind of see these rules in action. So before you move on here, it'd be really helpful. I have a pretest that there's a link here that is available in the description to this video below. Please take that. That helps provide feedback on how well this video does once we wrap up with like a post test as well. Okay, here are some of those definitive sources that I talked about. So the first one here is Zur and Iano, 2016. This is a really great paper. I refer to this a lot. It's a protocol for conducting and presenting results of regression type analysis. They give 10. And the reason why I didn't just sort of carbon copy this and just talk about this, as opposed to sort of develop my own set of rules, is this is nice, but one, it is for regression type, so it's not as broadly applicable to other types of analyses. And 2, some of the rules are a little more advanced. Mine are sort of pared down a little bit for a little bit more intro level approaches. Another great resource is Cass et al. 10 Simple Rules for Effective Statistical Practice. These again are really great, but they're less of like a step-by-step rules and more of a general considerations throughout your entire analysis. And I wanted kind of more like steps. Some other ones I didn't really use too much, but they're also useful resources in case you're interested, is this 10 Simple Rules for the Care and Feeding of Scientific Data by Goldman et al. And then the ASA has Ethical Guideline for Statistical Practices. So with that being said, without any further suspense. Okay, maybe a little bit of further suspense. Let's get to the rules here. Here are the 8 rules to tape to your forehead. We have annunciation, exploration, assumptions, building, testing, justifying, presentation, and finally interpretation. Now each of these, what I have done here is I have created a little icon of a body part to help stick each of these rules into your mind here. And I'll explain the selection process for each of these body parts as we dive into the rules in a little more depth. Rule 1, Annunciation. Clearly state your research questions. I used the tongue as a body icon for this because you need to clearly enunciate, speak out what you want to do. This is very important to do this before your analysis, not after, to have a clear goal or end in mind. This typically looks like something like 1 or 2 sentences. and being painfully explicit as possible. In fact, I was taught it's good practice to do something like, we want to test the hypothesis ... Like, we want to test the hypothesis that seabird abundance was influenced by temperature, vegetation, or precipitation. In fact, maybe you could be even more painfully office and say, we hypothesize that as seabird abundance decreased, temperature would increase, or whatever your variables are. It's useful to keep the identity of your variables in mind when you're doing this too. And in fact, you might even have sort of a ready-to-go template to fill this out. Like, we wanted to model y as a function of x, or see if x predicted y, or see if y was affected by x, and then just plug in the variables of your specific study to that. All right, so another reason why enunciation is useful at the beginning here is, in the end, you actually have to clearly state what you did, especially in, say, like an abstract in 1 or 2 sentences, and that's useful to be able to translate these into that written portion. So here's just a couple abstracts from top cited papers in 2020. Let's take a quick look here. Cas9 screening established T cell receptors recognized and killed most cancer types via this protein MR1, but not non-cancerous cells. So they could test the hypothesis that this receptor killed cancer, but not non-cancer. Here's another one here, a bunch of techniques to see that there was an independence of this stress-induced loss of these stem cells and immune attack and stress hormones. So they wanted to test the hypothesis that this event was independent of these events. And finally, a little bit more wordy, but we could see here that smoking was a major influence of mutational burden. So they were testing the hypothesis that, smoking was the major mutational burden, and so forth. And we'll have links to these studies if you want to look at them in more detail. All right, rule 2, exploration. This rule is get to know your data in and out. I used feet to represent this because that's what you use to explore. And really, the point of this is to be able to, if this is your data, you want to be able to explore it, go back and forth, up and down, kind of like those old like peanut cartoons with like the footprints across the yard. That's what we want to do. You want to explore your data as thoroughly as you can. And really, this is the most fun step of data analysis, in my opinion, because you don't have to make sure that you did the right test or the graph is pretty. You just get to just sort of play around and see what's there without having to be rigorous yet. And it helps inform what you're going to be doing. So some important bits of exploration is, first of all, summary statistics are your friend. So this is a great way to get a feel for your data. Things like, means, maybe medians, like standard deviation, range, all sort of things help get a feel for the average values of your data. Another thing, of course, is just graphs. Produce all sorts of graphs to help get a feel for your data. Scatter plots, bar charts, histograms, the like. I mean, the sky is the limit, and the oceans, abyssal plain, are the depths of where you can go in your graphing. Another important bit in your exploration is to be able to determine design and dependencies, because sometimes data, especially data like maybe you get from someone else or you didn't collect yourself, might have certain dependencies or setup that you need to keep in mind. That might not be obvious. So one good example of dependencies is some data depends on other types. For example, this is this data set here where they had 2 units of zones at different locations. We see here that these 4 locations are all nested in this mining zone here, where these locations are nested in this non-mining zone. And so at the individual level, there's maybe mother and child, but some of these observations are nested in this setup and some are nested in this setup, and that's an important thing you have to include in a more complicated design. So explore your data as thoroughly as you can. Rule 3, assumptions. ensure that your data meets test assumptions. So I used a bone here for this because just like in our body, assumptions are these hidden parts of statistical tests that need to be upheld for your body or your statistical analysis to be valid. It's a little abstract, but just stay with me on there. So assumptions, every statistical test has a variety of different assumptions, maybe like normality or independence or linearity, homoscedasticity, etc. that you want to make sure before you run your test, your data fits such assumptions. And you're going to check these at different points in time. It might be during the design phase of your experiment or before analysis, or sometimes even some work better after analysis. So keep that in mind. And assumptions help let you be ready to try different types of tests, because if your data doesn't meet some of test assumptions, you might have to try a different test. Like maybe you can't do a linear model, you might have to try a generalized linear model. And while in a perfect world, all your assumptions would be met and statistical analysis would be straightforward, that's very often not the case with real world data. So assumptions is a very important step in dealing with reality. Another thing to keep in mind here is you want to be able to use many pieces of information to test assumptions. There's a great article on the analysis factor, and I'll have a link of this at the end, that talks about unlearning certain statistical steps, and one of them is testing for assumptions. Some people are taught just, run certain tests for assumptions, and then if the test is significant, go forward from there. It's better to actually piece together multiple inferences, because assumption test is more of an art in many ways. Like instead of doing like a test for normality and be done, you might also look at a histogram, a QQ plot, and look at these inferences together to assess how well it went. And here's maybe an example of testing assumptions. A lot of times you look at residuals, and this is after the fact of analysis. You might want to try a couple different tests and then look at the residuals and compare and see if one test has a better assumption meeting than the other. So these residuals should have constant variance, be approximately normally distributed and independent of one another. And in this case, yeah, that looks good. All right, let's turn to rule 4, building. I used a arm, like muscles, because that's what you use to build stuff. So the rule is build one or more statistical models for your data. This is sort of a no-brainer type, but it's important to think of these as not just running a test, but like getting it set up, building it, getting ready to go. So the three things I think are kind of helpful in this building stage is model type, model equation, and model select. When I'm talking about model type, it's good to think about like what's the basic sort of type of model you're doing, like broadly. Like, is it going to be a t-test? Is it a ANOVA? Is it like a linear model, etc.? Having those sort of big picture idea in mind helps narrow it down as it becomes more complicated. Another thing here is the model equation. It's useful to be able to, even just in very generic terms, be able to sketch out like what your variables are, where they're going. So these are a couple examples from that Zur and Ieno. Let's get rid of that. They looked at different tests, but these are pretty complicated. Like, you can get this in depth about your model, very specific, very mathematical. In this model, they're looking at this variable RD, and these are all our X variables, and there's different subscripts and all this stuff to explain what kinds they are and distributions. You don't need to get in all of that right away. In fact, I don't typically get this much in detail. I have some sort of a compromise between a very basic, like, my Y variable equals, mx plus b, like a linear regression. I have something between this very simple one and a more complex like this. This one here looks at the number of calls as a function of like the different sex of parent, food treatment, and so on and so forth. So because this is what's kind of going on under the hood with writing a model in like a statistical software. So it's good to be able to at least have a rudimentary understanding of how it's set up, so you're entering it correctly and you're interpreting it correctly as well. And then finally, the model selection. A lot of times you have more complicated model. You maybe have a lot of variables, and maybe not all of those will be in your final model. There are different procedures. A lot of statistical software tests will have like a model selection procedure where you can load a bunch of variables and it'll take out variables that maybe aren't significant. So that's a useful step in sort of building your model. Okay, rule 5. We're on to the meat of this. The tuna and mackerel of it all. Testing. You want to test your statistical models on your data. So I have a hand here because you want to get dirty and really get your hands in it and taking care of it. So a very important piece of information here is start with the simplest model. Something like here, nice and simple shark. The easiest analysis, easiest interpretation. Don't do anything fancy. You can always build from there. So maybe you just have one y variable and one x variable that you think is the most important, and then you can make it more complicated as you go, add more variables, add more relationships, try different distributions, etc. And there are a lot of different methods of tweaking your models, adding variables, adding different distributions, offsets, so on and so forth. You can really trick out your model if you feel the need to. Another piece of information here is keep careful notes. It's very rare for anything but the simplest analyses to like just be a one and done. Often you have to do a lot of back and forth and try this and try that. And so it's important to keep notes of like, oh, what did you do? How did it work out? What did you do next? So you can keep a line from sort of your tangled mess of your analysis to your results, which hopefully are clean and clear, and go from all this sort of testing to a good result. Rule 6, justifying. This rule is justify your model results. And I have for this legs, because you want to have legs to stand on when defending your results. And this kind of goes hand in hand with model assumptions. A lot of your justification might just be, hey, yeah, it fit these assumptions for the statistical test. But there's also another component that often goes into it, is what's called fit statistics. It tells how well your model fits or tells your data. Common like measurements are things like AIC scores or like chi-square degrees of freedom. And there's other ways to do that. And a lot of times you might be comparing multiple models. Like AIC scores is very common for comparing different types of models, and the lowest score means the best fit, and so that might be a justification for using maybe a more complicated model compared to a simpler model. Another way to justify what you do is link to summary stats and research background. Like, remember, you probably did summary statistics like means or something. You want to make sure the results you got in your model like fit what you expected from like the summary statistics. Like if you had a mean of between like groups A and B, and when you graphed them, they really didn't look any different, and then your statistical test said they're very different, maybe something went terribly wrong. You want to make sure there's a matchup between them. And also you want to take a look at research background. Maybe you found something very interesting. Has other people found that in the research? Is there maybe a justification, or maybe is there even like a biological plausibility? Maybe say you found a relationship between some sort of y variable and x variable. There's a strong positive relationship. Like, is there a plausible mechanism between that you could find in the literature that would support these being a real relationship over and above something like statistical chance? So the bottom line for this is to have more or less have a why for each piece of the statistical process that you did, so that you're able to adequately defend yourself against anyone who would judge your analyses. All right, swimming later on here to Rule 7, presentation. Present your results through text, tables, and figures. I have an I here because a lot of this is visualizing or in some way transmitting the information to your reader. So the first step is text results, written results. So a lot of times is pretty standard, is a couple of sentences that includes your estimates. So a lot like means pretty commonly, test statistics, so a a t-value or an f-value, and then significance, that's typically a p-value. So like we found a significant difference between the means of males, 45, females 27, whatever value, and it was a t-value of 8 and a p-value of less than 0.0001, something along the lines of that. And we'll see examples of that in writing in a bit here. And that's going to be your primary results, and that's going to be backed up by tables and figures. Now, tables and figures should add clarity, not banality. And what I mean by that is they should add useful information that text alone can't provide. So good examples of that not working is, I was actually taught as an undergraduate that pie graphs are really bad for data visualization because our minds aren't good at interpreting percentages by pies. In fact, it can even be worse than that. There's things known as exploded pie charts. Not only is this bad, it's just incredibly bad. It's hard. I mean, you can roughly tell that this is the most, but some of these things, it's really hard to decipher out what's going on here. Another example of sort of not necessarily bad visualization, but just sort of not useful, banality, is something like a t-test. In general, you can probably just do that one text, and especially if it's not significant, you typically don't graph things that aren't significant. You can see here, these aren't significant. You could just said there was no difference in the mean of whatever y variable between group 1 and group 2. Now, a good example where graphs really do help is something like this. Maybe you have a couple different categorical variables. This might get kind of cumbersome to really parse out with text, or maybe you do have to parse out with text, but here's a clear summary of what's going on here. Now, finally, thing to bring in presentation is you want to make uncertainty a key feature, because statistics is not, this is what reality is. We couldn't observe all of reality, so we took a sample of it, and this is what our best estimate for reality is. So you always want to make sure your graphs have things like error bars, confidence intervals, or for example, in regression, you're going to have this regression line, but you want to have confidence intervals or of the mean or the data, etc. So with that, all right. Rule 8, interpretation. Clearly explain your results are and what they mean. So I have a brain here, kind of the final step of this process. So you want to be able to follow up numerical results with clear wording. So hopefully in your presentation you had a pretty clear, we found a significant relationship, here's the means, here's the test statistics, here's the significance. But then you might want to follow up with more clear wording, like as X increased, Y increased. Or if you have more complicated results, of course you'll need more text to clarify. Or you might need to explain your graphs, etc. To do your best of translating sort of the statistics, for lack of a better word, mumbo jumbo, to real world implication. What does this mean biologically? What does this mean scientifically, etc. It's also useful to relate this back to your overall goal, your research question. We had a hypothesis that we're trying to test that X was related to Y. Yeah, and we found within the results that, this was upheld, or maybe this wasn't upheld, etc. You also want to be able to project outside your study here of implications. On one end of it, you might have things like caveats or limitations, like why this study was difficult, or maybe the results aren't as trustworthy as you'd like. Maybe you had missing data. Maybe the data was just messy, or you only could collect some sort of data. It really kind of shows that you recognize the uncertainty in your data and willing to show how it could be improved. Now, on the more positive note, you can look at future, like what future studies, like maybe you found something really interesting. What might be the next step? What you found here, how could you explore that in more depth or translate it into something else here? Because really, at the end of the day, your data won't speak for itself. It won't explain itself. You have to be the one to put words in your data's mouth. Okay. Now let's reprise our rules again, because I want you to be able to stick this in your mind, in your head as much as possible. So we started with enunciation, which was our tongue. Then we explored with our feet here. We looked at assumptions as the bones, the underlying bones of our tests. We built with our muscles. We tested with our hands. We justified. So we have legs to stand on when defending our work. We presented so that the eye could clearly take in the results. And then we interpreted the results so that the brain can process what that means. Okay, with that, we will turn to our shark example. Just a quick overview of what this is. So this is from the data from this paper, A Global Perspective on the Trophic Geography of Sharks. This is the abstract. A lot of stuff going here, but the main thing is they have this this data set on carbon atoms, and then they took data from like over 5,000 sharks and looked at different species and a biogeochemical data set. So we'll look more into that. And here's just one of their graphs here. They looked at things like this. Again, this carbon ratio, we'll look at what that means. They looked at latitude, they look at habitat, and etc. So I'm going to turn to R, and we'll walk through this in more depth. All right, let's start moving and grooving on this example. So this is all going to be in R Studio here. So to get set up here, this data set is found on Dryad. And obviously, to do this yourself, you'll have to download it and load it in. So that's what I do here, and then a bunch of other libraries for different functions in R here. I'm gonna let them load here. All right, let's take a real quick look at our shark data set. So we got our names here. We have a bunch of variables: latitude, species, habitat, depth. This is length in centimeters. This is our variable of interest. We'll look at that in a second here. Carbon-nitrogen ratio, and then these are some other lipid extraction method. We're not going to deal with that. We're also going to deal with these. We'll look a little at this province code, sort of general location. And then this is the head. This is like the first 6 values. We can see, species is a category, latitude is a number, etc. And we'll dive more into this as we go on. So I'll start with enunciation here. So we're looking at D13C levels. So this is the ratio of essentially carbon isotopes. It helps give information, I think, on like diet and composition. We're not going to get worried too much about what that means. We're just going to use it here for this example. So the question I have here, I try to be explicit as I can to enunciate, is are these levels different across shark species or shark habitat variables? Another way to put this up would be the purpose of this study is to test the hypothesis that D13C levels were different across shark species. And I might also throw in the null hypothesis here, because why not? The null hypothesis is there's no difference across species. All right, let's jump into exploration here, number 2 here. Again, we have that summary. It's already here, so we're not going to do that again. So let's take a look at our continuous variables. So we're going to be looking at our D13C as our Y variable. So we're going to do a histogram. And this variable, again, is the ratio of 13 carbon to 12 cartine in parts per thousand. So we're going to do a histogram and then a QQ plot. So let's start with the histogram. So it's, roughly normally distributed, but we see that they're all negative values. So it's centered around like be like 12, negative 12. So that's important to note because negative values, we're not going to be able to do as much for some of these manipulations. And then a QQ plot kind of shows stuff here. It's pretty normally distributed around here, but then it kind of flares out the edges, which is sort of, we see here, it spreads out more on the histogram. All right, well, let's look at total length of the shark. So again here, yeah, it looks like it is actually right skewed, that most sharks are around this wide, but then there's some that are quite a bit longer. Again, you can see here it kind of stops being normal here. Normality for these are our predictor variables now, our X variables. Normality is an assumption, but let's just go look at the distribution as we go. Okay, our carbon and nitrogen ratio. And this is very interesting. So there's a lot of tail out here, but most are found around here. And we see here that there's quite a jump when it goes a little bit higher. Let's look at depth here. And this is, I'm sure, going to be skewed. Here's a QQ plot, but then looking at the histogram. So here, yeah, that it's sort of skewed. Most are found at very short depths and then kind of fall pretty uniformly higher out here. Which kind of makes sense. Is like if you're catching them, they're probably easier to catch at the surface. All right, well, let's look at some categorical variables. And so we'll do some summaries here. So there's over 100 species of sharks. So we can see these are the counts for species. So this first one, Pelagius, there's 58. There's some that are as little as even like 1. So we're not going to be able to look at all species. We'll probably have to do a subset if we want to look across species. Now, this providence code, again, there's quite a few. We might need to cut down on that. And then habitat is actually only 3 variables, pelagic, shelf, and slope. Now let's do some plots against our y variable. So these are going to be our continuous x variables, and we can see here. So we'll start here with length. It doesn't look like there's much interaction between length and our DC13 or D13C. It looks like there might be a positive relationship, or sorry, a negative relationship, but it might not be linear. It's hard to tell with carbon-nitrogen ratio. And then again, there doesn't look like there's a lot of any relationship, and there's a lot of variability up here. So next here, what we're going to do here, since we're not going to use all the sharks, I'm going to just take the top 4 species. P. glauca, C. plumbus, S. lacatus, and S. acanthus. And just essentially subset that and then plot it by our D13C, and we can see, oh yeah, it looks like there is variation and some differences here. We're going to do the same, but we're going to use 6 provinces because heck, why not? And again, looks like there's some variation. It looks like this has some of the highest values, and this has some of the lowest. But more even sort of variation between like the size of the bars. Okay, and then again, we don't need to do anything with this because there's only 3, so we look at habitat. They look pretty equal, though this has a lot of variation for the shelf. Next, we want to do some correlations because if we're going to use continuous variables, if they're highly correlated with each other, we shouldn't include them both in the model, so it's important to check those. Let's see. Oops, sorry. Okay, and this is one way to plot correlation. So first, this is our y variable. It's nice to see just how sort of correlated, how much relationship there might be. Looks like the strongest one is carbon nitrogen. Not surprising because this is also stuff with carbon. It looks like depth is quite a bit weaker, and there's almost none with length. But the important thing with correlation of like adding this to a variable is looking at the interactions between the x variables. So like Cn and length, depth and length, and then Cn and depth. And it looks like these ones here, they're a 0.8, either minus or positive. It's sort of the cutoff. Like these are nowhere close. Like they're not correlated with each other. There's not multicollinearity. That's an assumption of multilinear regression. So we can safely use any of these continuous x variables along with each other. So now let's look some more about the design dependencies. So again, we look at sharks. To look at this, I want to look at habitat and provenance code. So So we made this data set up here we called Shark Top, which just has the top 4 species. I want to take a look at how species and habitat interact. Oh, and it looks like here, this is important. Looks like habitat, like these species have one habitat. So 3 of these species are on the shelf, the other 4 is in pelagic. So it doesn't make sense since habitat so much depends on species to include them together here. So I don't think we'll use habitat in our analysis. Let's look at our provenance codes, and we can see again, it's a little different here, but we can see that 2 of these species just have a single location, but then these other species have a bunch of different locations. Now, if all of them had a wide range, it might be useful to include the provenance code, but since there's sort of like this dependency that some are just in one place and others in different places, we're again, just because we kind of want to do a simpler analysis, we're not going to try to untangle all of that. That seems like sort of biased dependencies here. Okay, well, let's move on to assumptions. Now, we've already kind of seen some of them, but let's start with the Y variable. A big thing here is normality. Now, you could run something like the Shapiro test. That's a test of normality, and because it's significant, that means there's significant reason to believe that it's not normally distributed. It's a little confusing, but heck, that's just what it is. Though, again, we want to use multiple pieces of information, so I'll look at the histogram. Again, it's like, and this is for that subset, so it's not the full set of data. And it's still pretty normally distributed. It's a little off here, but I think it's good enough for what we're trying to do here. And again, we'll do a QQ plot. Again, yeah, kind of the edges are a little flared, but, you know, for our purposes here, it's going to be good enough. Again, if you're doing this for publication, I'm not sure, I might try to do more analyses here to clean this up, but again, I'm not publishing this. I'm just trying to give you a nice example with sharks. So let's move on here. So X variables. So if we're using continuous variables, that's going to be kind of regression type. We want to look at things like linearity and homoscedasticity. So again, we're going to kind of plot this carbon and nitrogen. It kind of looks like this is the subset again. It looks like it might, I think it's probably linear, but we might want to try to log transform that, see if that cleans it up. And we do a little bit better, but not enough that I think we need to worry about transforming it. I think we can just keep the yellow. Another thing we can look at here is homoscedasticity. Is like, is there variation the same across all variable? Is Y variable across same sort of variability across X? We can see here that that's not exactly the case. Even in either of these, there's a lot more variability at the bottom end than as you go up. It kind of gets a lot more even. So that's important to keep in mind. Let's look at our other continuous variables. So first with length, same sort of thing here. There's a lot more variability here than here, so that's kind of a problem that sort of violates homoscedasticity. But for now, we'll kind of keep it on. We'll see what happens. This is interesting because like depth, where it seems like it's pretty not really evenly distributed at all, and there's a lot of variation here, and it's like all the same variables, so there seems to be a lot of issues here. So we'll keep that in mind as we move forward with both depth and length. Now for our, not our continuous, but our discrete variables, our categorical variables, sorry, not even discrete, categorical, we're going to look at species. Oop. And again, we saw here that the assumption we're testing is homogeneity variance, so that like these bars, they should all vary about the same or not be too much different. Looks like there might be rule of thumb is like 3, so like this looks like this is about 3 times at least or more a variable as this. So not sure homogeneity of variance is upheld. And again, we can do a specific test like the Bartlett test. This is significant, so it means that there's significant evidence that homogeneity is not the case. So again, maybe we could transform this or something like that, but for now, I think it's not wildly, ridiculously out, so we're going to say that's good enough for now. All right, model building. So first of all, some wording here. The model type is, I think there's going to be something along the lines of a linear model. We're going to have, we're going to have both categorical and numerical, so not quite a regression, but we'd say more of a linear model. I mean, there's potato when it comes to like definitions, but just let's keep moving on here. Model equation is doing something simple. D13C is a function of, so our essentially intercept, our species, and then depth, length, and carbon nitrogen. And we're going to do just model selection and see if there is any variables that maybe we want to take out. So we start with a full model, and we're comparing AIC scores. And when we take out, it turns out when we take out depth, the model gets a little better, the AIC goes down. But then after that, doing nothing is the best model. So the best model it gives us is all these ones minus depth. So we're not going to include depth in our final model here. So let's move on to testing. So let's start with our simplest model. We really care the most about species. So all we're going to do is create and we have our top 4 species. So Carcharingus, Priyanka, Scoliodon, and Squalus. And we're going to model that as a linear model here. And this is our outcome, our summary. We see here that it was significant. And there's a lot of places to look here, but first of all, we have our test statistic, our degrees of freedom, and our p-value was significant for the overall model. And then if we look at the individual species, so this is comparing each species to the default, which I guess is going to be our Carcharingus, because we don't see it here. So it's these 3 are all significantly different from that Carcharingus. Now, if we do a fuller model where we add the length and carbon nitrogen ratio, we can also get a thing here. And this is what we get in the end here, but it's interesting. So this was significant, length was not. But it was interesting here and troubling is we actually only see 2 species now. So we're just comparing this species to the first and this species to the first. So there's only 3 species, so we lost a species. Well, what's going on here? Well, it turns out there's an issue with missing data. We view the sharks here. We could view that, but there's still so much data. First of all, like right off the bat, we see that Priyanse has no variables for depth. And there's other missing variables too here. In fact, we can use some plots here to kind of visualize a little bit more. So like for this first one, we found that, yeah, most of the depth variable across all observations are missing. I think there's just like 1 species that has good depth variables. Also, it looks like the carbon and nitrogen ratio has a lot of missing data. There's a little bit of length data missing, but for the most part it's not. And then we have all the D13C data. And we look more so across species. It looks like we have a lot of missing data for Carcharingus, really none for Scoliodon, and then middling for this. So at that point, because we have so much missing data for these variables, we're just going to use the final model with just species. And then from there, to do a little more testing, since now it's essentially an ANOVA, because they're categorical variables, we can change our linear model to ANOVA, get more of an ANOVA outcome, which usually just has, hey, the model is significant, here's a significant variable, and then you have to do a post hoc test to tell which variables were significant. So we'll do a 2-key test, and then in fact, just plot that. And then this is really a useful thing. It compares every species against every other species. And we can see here that since none of them overlap the 0, they're all significantly different from each other. So great. Now let's look at justifying. So again, we can kind of plot this, do some plots of the residuals. So residuals don't work as well with categorical variables, but we can kind of do that. It looks like it's okay. Not pay too much attention because again it's categorical, not really regression style. Normal plot looks pretty good. I usually don't look at these other ones we saw that our assumptions weren't quite met. So like, I'm not sure how much we could justify this in a fancy paper, but we're not doing that here. So I'm going to say that it's good enough. Now, if we had multiple models that both worked, we could look at AIC scores compared to each other. But since we don't, we only have really one viable model. That's what we stick with. All right, with presentation. Now, sometimes it's hard to plot stuff in R. Actually, just create a function that I can get nice, quick summary stats. And then we can call that on our data set. And essentially, I'm able to get my means across the species and then upper and lower confidence intervals. And then along with the summary statistics that we had, here I can pull out data to get sort of the text part of the portion. I could say that mean D13C values were significantly different across all 4 species. Then our F value, and we typically have our degrees of freedom, 3 and 976. That was 138, and the p-value was less than 0.0001. And then the follow-up to kind of explain more is like S. anthracis had the lowest mean value, and here's our mean. That's our estimate, followed by Plummus, Glauca, and Lasidius. I'm mangling these scientific shark names. Just bear with me here. We don't really need a table for this information. I'll leave that out, but we could do a plot here. And I can have a nice GG plot here to kind of show this here. And it's nice. It shows us that Squalus acanthus has the lowest values. Scoliodon has the highest, and these are intermediate. And now, just because we're dealing with scientific names and we have no idea, I for a little treat for you, I actually pulled up images and I can plot them with their scientific and common names. I'll show you what shark species we're actually looking at here. And this is useful for not only results, but possibly interpretation. So these are our species we have here. We have a sandbar shark, spade-nosed shark, spiny dogfish, and blue shark. These are pretty common species, not surprising that these were the most caught here. And they all had different D13C values. An interpretation here, you might have something along the lines of this. Our hypothesis was correct, so really back to our initial Annunciation. D13 levels were significantly different across 4 of the most common species of sharks from the BERD et al. Shark dataset. And then here's some kind of caveats. Given the missing data and contingent nature of some of the variables, we were not able to use other variables such as length, depth, habitat, or geographical area in the final analyses. So there you have it there. That was an example using shark data. With that, I'll wrap up here. Last couple slides. Really, I hope that these rules will help stick with you on your statistical journey. Before you finish here, please take a post-test and survey that helps get feedback on how well we did here. The links are found in the description below. Here are the references that I kind of mentioned through, the different rule references, example abstracts, and then just various other sites or picture references, and then the shark data that I use in the example. Finally, acknowledgements. This is supported through the DaCCoTA grant, part of NIH. So please cite us if you found this useful. Thank you for joining with me, and have a great day.